Afternoon, everybody. My name is Will Potts. Today I'll be talking about materials to minimize distortion in precision devices. An example of precision device that we're going to be talking about is sub-micrometer displacement gauges, and the part that we're actually going to be trying to minimize the distortion is the force loop, which is this portion here, which holds the probe. So our design is going to be limited by the distortion due to temperature variance and instrument vibration. So our material must be able to tolerate heat fluctuations and the vibrations, which would maximize the accuracy of the device and minimize the distortion, with our free variable being the choice of material. We start out with the heat input per unit area, which is the thermal conductivity multiplied by the temperature gradient. We can then use the strain equation, which is the thermal expansion coefficient, and the ambient temperature, which is the temperature difference of the operating temperature and the ambient temperature. And then we're going to combine those together. We find that the distortion is proportional to the strain gradient. Once we have that, we can get our first material indice that if we have a given geometry and heat flow, the distortion will be minimized using this equation here, which is the thermal conductivity over the thermal expansion. Second material indice would be the sensitivity to external excitation. We need to minimize that. It's basically saying we need to minimize the amount of internal vibrations. The highest possible natural frequencies are what we're going to be looking for, and then flexible vibrations have the lowest frequencies and are proportional to our second material indice. On our graph here, we want anything down in this search region. We have our thermal conductivity over our thermal expansion value set to 10 to the 7th. That gives us values such as silicon, silicon carbide, and tungsten carbide. And then for metals, we have copper, tungsten, and INVAR down here. So the problem with our INVAR and a lot of our other metals is they have high density, which would make our N2 value unsatisfactory. If we move our line here, we can see that the silicon carbide and the INVAR have similar properties when it comes to our first material indice, but silicon down here is the best on our graph here. That means that silicon will be our best choice. It is available in large sections and it has high purity. Our silicon carbide is a good second choice, but it is more difficult to shape than silicon. If you wanted to build something that is cheaper and much easier to shape, aluminum alloys here won't have the quality of our silicon or silicon carbide, but it will be much cheaper. So in summary, we were looking to maximize the accuracy and precision of our measuring devices. Our material that we selected was silicon, with silicon carbide being a second choice. The rationale is that it's low density and it has minimal thermal distortion. And concluding remarks, for the force loop, silicon was our best choice, but the aluminum alloys would be an alternative for a cheaper and easier made or shaped item.
Alright, Taylor Reeds. I'm doing the design project on nylon bearings for ship rudders. Typical bearing is made out of bronze, which is good against wear resistance and resistant high pressure situations. But we're looking for a new type of material to use on them that could possibly have more wear resistance than that, because typically the wear that happens on bearings is due to sand, fretting from vibrations. It also has to do with galvanic corrosion, which is metal-metal contact along with electrolytes. The model description that we're going with is basically, this is the pressure. The force, we're going to say that is already subscribed to it basically from the design of the rudder or the ship itself. The only thing that's going to be changing that this is dependent on is the area, which is basically the diameter of the bearing and the length of the bearing. The way that the case study went over it is M1 and M2. M1 and M2. M1 is for the wear constant Ka. M2 is the wear constant times the hardness of the material. And as described in the case study, the one with the lowest Ka, when there is no change in the sizing, would be the lowest M1 value, or material index 1. And for M2, It's exactly the same, except in this case you are resizing the bearing. So with this resizing, it's the lowest value possible, which would be PTFE over here. In their conclusion, they said that the company actually picked nylon 6, which is an unfilled polymer, and they recommend a polymer that is filled with nylon, similar to nylon, and that would decrease the damping, which would make it where it's less malleable basically, and it would increase the wear of it. Some other options are glass reinforced PTFE and other materials filled with nylon and things like that.